Okay, so this time I will be talking about transition-based parsing with neural nets. So there are two types of linguistic structure that we often use. I guess I probably should have said syntactic structure, but we have dependencies, which you read about in the reading materials. These focus on relationships between the words. So we have something like this, where we can say saw is the head of I, girl, and with, and then with is the head of telescope, etc. And then we also have phrase structure, which focuses on the structure of the sentence and what all the phrases, the kind of the roles of the phrases in the syntax of the sentence, etc. And these have very different structures and very different roles. Does anyone have an idea? Let's say you want to use parsing in your downstream task. Which one of these should I use for my task? Any ideas about that? No? Is anybody using parsing in a task? I don't want to make you embarrassed if you're using the wrong type. But what type of parsing do you use in what task?
I think I use both.
You use dependencies and phrase structure, and what is your task?
Well, just use to extract features.
To extract features, but what do you try to predict?
For phrase structure, I mean it's easier to get head words and stuff.
For phrase structure,
No.
For dependencies, it's easier to get head words actually.
Well, yeah, we can talk about it.
So for dependency trees are actually quite useful for a lot of, or trees are actually quite useful for a lot of things, but in general, my interpretation is that dependencies are better for semantic tasks usually, and phrase structure is better for syntactic tasks where you need structure of phrases. An example of this would be stuff like question answering. Usually dependencies are a better choice because they tell you like what is the subject of this. So if you want to know who did what, it's easier to get that from dependencies, although of course you can get it from phrase structure as well. If you're doing something like translation where you want to be reordering phrases in the correct order, for example, it's often better to use something like phrase structure because this tells you about the structure of the sentence and reordering and things like that. But you can also get that from dependencies. So it's not necessarily the case. Yeah.
Sorry. So do you think that dependency structure captures more semantic information than phrase structure? Like, but for most dependency tree the structures are deterministically transduced from the phrasal structure.
That's a good question. The question was, I said that dependency structure captures more of semantics than phrase structure, but for most dependency tree banks, they're actually converted from phrase structure. So that's a good point. I think phrase structure is generally more rich in many ways. You can, for example, tell, in some cases, you cannot deterministically tell what the phrase structure is from the dependency structure, but in most cases, you can do it deterministically in the other direction. But the thing is, dependency structure shows you like the subject and the object in a much more direct way. There's a single link between the subject and the object of a sentence. There's a single link between a single link between the verb and the subject of the sentence, a single link between the verb and the object of the sentence. So if you want to do something like create a representation of the verb based on its subject and object, it's really easy to do with dependency structure. But if you do it with phrase structure, then you basically have to write those deterministic rules yourself in your model to do that. So it's not impossible to do with phrase structure, but it's just a lot more natural to do it in dependency structure a lot of the time. Any other questions? Yep. I see people who either look confused or are doubting what I'm saying here. If you have something to say, feel free to ask. Yeah. Yeah.
Is one better than the other to alleviate this ambiguous parses?
Is one better than the other to get basically, is it easier to parse one than the other? I don't think it's really that much easier, but if you can parse phrase structure, you can get dependencies. And often phrase structure parsers, if you get a phrase structure parse, run your deterministic dependency extraction rules and evaluate the accuracy of the dependencies, then you actually get better dependency parsing scores from your phrase structure parser. So I think it might be safe to say that phrase structure parsing is a harder problem, but we have better methods for it, so we tend to do a little bit better at it. I think many people would disagree with me, but that might be a good summary of the situation. But I think they're basically the same in difficulty. All the hard things for phrase structure parsing are also hard for dependency parsing. Anything else? Okay. So parsing is predicting linguistic structure from the input sentence. And there's two methods that I'm going to talk about here. One is transition-based models. And they step through the actions one by one until we have an output. And if you want an analog of this is like the history-based models for part-of-speech tagging that I talked about, like the teacher forcing models or the history-based RNN models. And basically, yeah, it's like that. I wrote graph-based models here. Actually, I'm going to talk about these next time, and I actually changed the name to dynamic programming models. So these are models where you don't actually only make predictions with your neural network. You also have some sort of dynamic program on top of it. So yeah, we calculate the probability of each edge or constituent and then do some sort of dynamic programming to decide. And this is like the analog of this is our linear CRF models that we talked about last time. So you can kind of think about these in very similar ways. Although the algorithms are different, the basic idea is the same. But this time we're going to talk about transition-based models, and I'm going to talk about shift-reduce dependency parsing models. So yeah, why dependencies? Dependencies are, I kind of already said this, they're often good for semantic tasks because related words are close in the tree. It's also possible to create labeled dependencies that explicitly show the relationship between words. So if you want to know, let's say you want to know all the things that could be a object of saw, you could just take all your dependency trees, grab all the links that say direct object, and you could get saw girl, saw dog, etc. So arc standard shift reduce parsing is you basically process words one by one left to right. This is just reviews. So we have the queue or the buffer, the stack. At each point, choose a shift, a reduce left or a reduce right. And we learn how to choose each action with a classifier. So we can get a tree like this. So the nice thing about this method is now this is just a classification problem, like all the other problems that we did before. We know how to make good classifiers. So let's try to make a classifier to choose shift, reduce left, or reduce right. And this is an example. I'll be using this running example. So I saw a girl, shift, and stack. And on the left side, we will be having kind of open trees that we have not finished yet. If they're in the head of that tree will be in bold. On the right, we have the buffer. Wait, that's not shift. I'm sorry. That's a reduce left. Sorry, my actions got desynchronized here. So, this is reduce left, and then shift, and then shift, and then reduce left, reduce right, and then we have our tree here. So this is what our example looks like. Okay, so classification. How do we do this? I think this wasn't really covered very extensively in the reading, but basically we have a configuration. Based on this, we want to choose an action, or I guess the problem was there, but the methods were not described so carefully. So then we want to choose shift, left, or right. And so basically what we want to do is we want to extract features from that configuration. And the kind of features that we can extract are what words are on the stack or buffer. For example, what are their part of speech tags? What are their children? And also one really, really important thing for dependency parsing is that feature combinations are important. So just as an obvious example of this, the second word on the stack is a verb and the first word is a noun. If the second word on the stack is a verb and the first word is a noun, then the right action is very likely, because it's very likely that we have, for example, saw, and then dog, and we'll want to draw a dependency link between them. So you know, we can make combinations of these features, and these combinations of these features help us classify accurately. But the problem is it's really hard to create good combination features manually. And for example, this paper, Zhang and Nivre 2011, increased the accuracy of dependency parsing by several points just by engineering better combination features. They didn't change the algorithm at all. They just went through and hand engineered all the stuff that they thought would be useful and threw it into the model. But now, fortunately, we can use neural nets, and neural nets are good. If they're good at anything, they're good at basically extracting combination features for us. So here's a first attempt. This was the one neural model that was mentioned in the reading, but it was mentioned extremely briefly, so I'll talk about the details here. Were there any questions up until now? No? Okay. So this is a model for, it's a feed-forward neural model for dependency parsing. And the idea is basically that we want to choose our shift or reduce left or reduce right actions based on the stack in the buffer. So from the stack in the buffer, what we do is we extract features. These features can be about the words or the part of speech tags or the arc labels. These arc labels are basically they're doing labeled dependency parsing here, so they have information about the arc labels. They run these through a hidden layer, and then they run a softmax where they basically choose shift or reduce, or reduce left or reduce right, and then they let the neural network do the feature combination for them. So what features do they extract? They extract the top 3 words on the stack in the buffer. And then they use the word embeddings from the top 3 words on the stack in the buffer. They extract the 2 leftmost and rightmost children of the top 2 words on the stack. So S1 is the top word on the stack. LC is its left child, or SI is its SI is the ith word on the stack. LC1 is its first left child. LC2 is its second left child. So they extract all of these. This results in 8 vectors of features. Then they do the leftmost and rightmost grandchildren with 4 features. And then they do the post tags of all of the above, 18 features. And then all of the ones that are children are 12 features. So they do a bunch of feature extraction, and then they combine these together. So does this strike anybody as a little bit strange here? No? So the reason why this is a little bit strange is the whole reason why we want to do neural networks is so we don't have to do feature engineering, right? And I just listed a whole bunch of feature engineering that this paper is doing. So this paper is halfway in between the neural network revolution and the old style thing. So what they're doing is they're extracting a lot of things that might potentially be useful, then they're letting the neural net learn the combination features. They're not completely foregoing feature engineering, but they're letting the neural net combine the things together in the appropriate way. They also have a nonlinear function. This nonlinear function is the cube function. This is strange, or it's unusual. So what they do is they basically take the cube of the input vectors. So what that looks like is this. They basically take all of the features and they multiply these by a weight vector and a weight matrix, and then they take the cube of this. And this is a kind of strange function if you think about it. So they're basically cubing. They're basically cubing the values of things added together. Has anyone taken a look at this paper and know why they're doing this? Yeah.
Cube actually looks similar to an activation
It does look similar to an activation function. It looks kind of like this. It's like the opposite of our normal activation function. So the normal activation function is like this, right? This is our tanh, and this is our cube. So that's a good observation. So why does anyone know why they're doing this based on this? Yeah. Okay, so the answer here. Do people know about support vector machines? So in support vector machines, we have something called the polynomial kernel, which is basically a thing that combines all our features together and takes and multiplies like x by y by z. And the idea, I think this might have been motivated by this, and it kind of seems like what they wrote in the paper it was motivated by this. But basically, if we can have a way where if all three of any are active, then it will make this feature active. So this feature function here basically can say, okay, if these three features are active, we will make this extracted feature active. So you can extract these combination features that are combined up to three different features combined together. Was the motivation that was written in the paper anyway. They did experiments and showed that this worked better than anything else. I've not really seen anybody else use this since then, so I don't know if it's easy to apply to other problems, but it might be one thing to think about using. Yeah. Oh, and here's the equation that they cited there. So you can do like weight. It's equal to this, so you can extract things where three features are basically multiplied together. And with their result, I won't give all the numbers, but basically this was in 2014, and this was really fast, 1,000 words a second. It used a nice pre-computation trick to basically cache the matrix multiplies of common words. This was also used in a thing, but basically the idea here is if we're extracting features like this, XW is XW is an embedding of a word. So if you take the top 10,000 words and pre-compute XW times the weight matrix for all of those words, you don't need to compute that anytime you get one of those words there. And this sped up, this pre-computation trick sped up their parser by a factor of 10, I guess. And also they got strong results beating most existing transition-based parsers at the time. So this was kind of a big thing, I guess, a couple of years ago. I have a let's try it out code walk here, but I'm actually going to skip this because it's almost exactly the same as the thing I'm going to talk about next. And the thing I'm going to talk about next is more interesting, so we'll talk about this. But you can take a look at the code. We do have the code there. So any questions about that so far? I think it's pretty straightforward. Okay. So now I'm going to take a break from parsing for a second, and I'm going to talk about tree structured composition. This isn't only for parsing. This is if you want to use parses in any of your models. So it could be used, it is used in parsing, which is why I'm talking about it now, but it's also useful for classification or whatever else. So why tree structure? Why would we want to use tree-structured composition? And basically the idea is it can go back to something like this, which I showed maybe in the fourth class or something like this. This is the sentiment tree bank that Stanford created, and basically you can see that different parts of the sentence kind of have a coherent sentiment. So the empire lacks in depth, but it makes up for it in heart. So the idea is, if you look at coherent phrases, they kind of have a coherent semantics. They have a coherent sentiment in this case. And if you combine them together, you get a very natural. You can come up with a very natural way of saying, like, negative sentiment but positive sentiment. And you have a tree that looks like this. And if you have something that's negative sentiment but positive sentiment, then you're pretty sure this is going to be a positive sentiment overall. And if you have this tree structure, you can actually you could almost write a rule-based system that would do this for you. And anything where you can write a rule-based system that can do something for you, it's probably really easy for the neural network to learn this. If you have to throw everything into a big LSTM that learns how to parse the sentence while it's learning how to do sentiment analysis, it's going to be a lot harder, and you're going to need a lot more data to learn that thing. So that's kind of the motivation for using tree structure when you're calculating representations of sentences. Any questions, comments? Okay. So one way to do this is, these are called recursive neural networks. I actually like to call them tree-structured networks because it makes it more clear that they're trees, but in the original paper they were called recursive neural networks. There's actually another paper from 1991 that has almost exactly the same figure in it. So these are not new, but this paper was the one that showed us that they work well in modern settings, I guess. So yeah, it basically looks like this. If you know the tree structure of the sentence in advance, you can compose things according to this tree structure. And you can do it with a function that looks like this, where you take the representation for the left child and the representation for the right child, multiply them by a weight matrix, and then add a bias and take a tan H. So each of these tree RNN, the left one is H1, the right one is H2, and we compose things according to this. Any questions about this?
How do you decide the structure?
Oh, so sorry, that wasn't clear. I'm assuming the structure was already given in this case. So we already had a parser that gave us a parse tree, and we calculated this. So in this paper, actually, they already had this structure, and then they used that to do sentiment analysis. I will talk about next how we use this while we're doing parsing also. Any other questions? Okay. You could also do something like parameterize by the constituent type. So you might have different composition behavior for the noun phrase or the verb phrase, for example. So we might make this W a W specifically for noun phrases, a W specifically for verb phrases, or whatever. And that could allow us to do things like noun phrases. We know the head is usually going to be on the right, so we want to consider the stuff on the right more. Verb phrases, the head is usually going to be on the left, so we want to consider the stuff on the left more, for example. So that paper was all the way back from 2011, which is like 7 decades in deep learning time. So now we have better methods like tree structured LSTM. So tree structured LSTM is there's kind of 2 varieties of this that were presented in this paper. One is the child sum tree LSTM, and the idea is basically we share a single set of parameters based on between all of the children. They might be based on grammatical label, etc., but usually they're just shared. And then we have an LSTM-like function, but we have a forget gate that is different for each child. And what this means is that the network can learn to ignore information from particular children and give more weight to other children. So intuitively, this is something like we have 3, or let's say we have 4 things in a noun phrase, and it's like the big bad wolf. And each of these has its own vector. We will run something that looks like the LSTM update function, and we'll get a new vector up here for all of these. But then we have a forget gate value for all of these, and if the forget gate for the left one is 0.95, 0.8, 0.8, 0.1, it will take this with a larger weight, a weight of 0.9, so it will mostly use the information from this one over here, but it will also use a little bit of the information from the modifiers and just throw away the information from the determiners. So kind of linguistically, this is interesting because it could, learn to remember or forget based on which parts of the tree were more important. The other nice benefit of this is this applies to any number of children. You can use this, if we had a noun phrase that had 15 modifiers, it could still handle this, basically. Exactly the same as the other one. On the other hand, it doesn't have any information about the ordering of big and bad, actually. So if big and bad are in the opposite order, the bad big wolf, that means something different than the big bad wolf, I guess, probably. So this doesn't have the capacity to capture that.
But if you had a tree structure, wouldn't the order be explicitly specified by your tree structure?
Well, so it is, but this model is ignoring that. So it's calculating each of these updates independently and just summing everything together. So the second one is the N-ary tree LSTM, and this is you have different parameters for each child up to n. So this is like the tree RNN, but this time you have different parameters, so you can handle stuff like ordering as well. The only problem is now number 1 and number 2 are completely different. So in this case, the big wolf would have a completely different calculation function it would have a completely different function to calculate for wolf than the big bad wolf would. So it's kind of a trade-off between these two. And then finally, there's another one which is by LSTM composition. So the idea here is you have any number of constituents, and instead of running them through this simple tree RNN function, you take a bidirectional LSTM, you run it in the forward direction, run it in the backward direction over all of these vectors, and you calculate representations, and then use them as the representation for the next layer. So this is kind of giving up, right? We're not going to design any beautiful tree structured LSTM. We're just going to assume that our regular LSTM is good enough, and it can automatically learn how to compose stuff together for us. I don't think any work that I know of has actually compared these two together, but I kind of like both of them. I like this one for its design and intuitiveness, and this one because it's really trusting neural networks are good at doing things. So, whichever one suits your taste, I guess, is the one you should be using. Are there any questions? This one we have a quick demo of. Okay. Which one was it?
It's a
Tree parser. Okay.
yeah, this is just the Socher and type of
Okay. There you go.
Okay. Is this big enough for everyone to see? That one, or are you okay? Cool. So here we have both the Socher and type papers. So let's parsers. So let's look at the Socher one first, I guess. So you read in all of your data. This is boring. Let's get that. So this is the main function for the Socher paper. What you're doing is you're sort of recursively walking through the tree until you hit a leaf. And then when you have the leaf, you're sort of going back down the tree and then doing all the compositions. So you can, if you look here, this gets the two children, then you compose them, get the representations, multiply by the weight, send it through a tangent, return that. Otherwise, if it is a leaf, you return the lookup of that expression. And yeah, this one's pretty simple. Any questions about that? I think it should be fairly straightforward what's going on. Awesome. So the next one is the tree LSTM. And here you have a lot more parameters, but you're sort of doing the same thing where you're walking through the tree and composing them, but instead of just doing the simple composition, you have what you're basically your entire LSTM function here. So you concatenate the two children and then run it through the LSTM, essentially. Do I need to go through each of the functions, or is that good enough?
I think so the main interesting thing is you see you have a different forget gate for each of those.
Right. That's cool. Yeah.
And this is a binary tree LSTM because all of the trees in this data set are binary trees, so you're fine with doing this. If you have actual parse trees that can have multiple constituents or dependency trees, for example, you would need to add either add additional parameters to your n-ary tree LSTM or use the child sum tree LSTM.
So how do you handle the children, the leaves?
So for just the leaf handling is the same as the previous one, where if it's a leaf, you're just returning the lookup for that.
Oh.
Yeah, sorry, I sort of skipped that because it is the same.
So what's the second case?
The second case is when you have one child, so
Oh,
already,
okay.
and it's just the composition for that, yeah.
It's not a binary tree.
Right, it's sort of building up to the point where you get to a binary tree.
I thought it was a binary tree. I don't know why this is here. Maybe I was missing a unary. Like maybe the non-terminals are unary or something like that, or the pre-terminals are unary.
Right.
Yeah, if it's a pre-terminal, so you are learning a function from an embedding that you also learn. Like learn a function from your one embedding.
Yeah. Right. Directly. Yeah, that's true. I have to admit I reused this from something I did we did a long time ago, so I actually don't remember why we had this here. But, any other questions about this? No. Okay, I will go on to the next one.
I actually have one question on violence.
So, oh, sure. Yeah.
How do you exactly? What is your output exactly on each vinyls?
So the output is basically a vector that is the same size as the previous vector.
So I mean, basically, you're just getting two binary trees, or
so the input to the LSTM is the representations of all the children.
right.
and the output of the LSTM is the representation of this node itself. You see what I mean? So every node is a vector of, say, size 512. You run that through a by LSTM, and then you take the last state of both the forward and backward LSTMs. You concatenate
so
them.
You just get the end.
Yep, yeah.
So you can take the end reading as well, if you do that.
By LSTM, this can handle any length,
Yeah.
and it could learn, more. It could probably learn more flexibly than this, I guess.
Right.
Cool. So I'll move on to the next one. This is a parsing model. This parsing model is both pretty elegant and quite successful. It also uses tree composition as part of the model, which is why I introduced the tree composition first. So I mentioned that we didn't want to do feature engineering. We didn't want to do feature engineering in our parsing model. This model is a way to do prediction without doing any feature engineering. So the way it does this is by, instead of engineering features, it tries to encode everything with a recurrent neural network. And the information that we have to encode is the stack in the buffer. One thing that was not used in the previous work is whether we just did a shift, just did a reduce, just did a reduce left, or just did a reduce right. So the previous work didn't directly use the action history in its calculation. So this one can also use the history of past actions. So the way we do this is we basically take three RNNs. One RNN is in charge of encoding the stack. One RNN is in charge of encoding the buffer. So the stack is the things we're parsing right now. The buffer is the words we haven't seen yet. And the action history is the shift, reduce, left, etc. And it just combines all of these representations together and makes a prediction. So the top right one and the bottom one are completely straightforward. This is just a regular recurrent neural network. And we don't need to think about this. We already know how to do this. The one on the left is a little bit more tricky, right? We have a tree here. And this tree is included in our is input to our recurrent neural network. So we can embed words. So the key insight here is that we can embed words, but we can also embed tree fragments, right? So I just showed you how to embed tree fragments. We have stack LSTM, or sorry, we have tree LSTMs, or we have a by LSTM composition function that we can call recursively. And this particular method is using the by LSTM composition function to compose these trees. So the contents of a buffer are basically this sequence of embedded words, which we periodically shift from. And the contents of the stack are a sequence of embedded trees that we periodically pop from and push to. And because these are sequences, we can use an RNN to get the encoding. But what we don't want to be doing is run the RNN over and over and over again. Because if we run the RNN over and over and over again for every parse configuration, this would be a huge waste of time, right? So there's a kind of neat trick about implementing this efficiently. It's called the stack RNN. So basically, it's an RNN with a stack pointer. So like a stack, you can push or pop, push to it or pop from it. And it has three constant time operations: push, pop, or embed, or return the embedding. So return the RNN state at the location of the stack pointer, which summarizes its current contents. So the way this looks, this code up on the top right is from Dynet, but we start out here with a null stack. We push something onto the stack, and then we pop it from the stack. We push something onto the stack, pop it from the stack, and then maybe push push something back onto the stack. And this is what we would want to do if we basically did a shift, and then we did a reduce, a shift, a reduce, a shift, a reduce. So if you think about it, every time we reduce, we need to create a new thing on the stack, and it's going to be different from what we used before. So this is a way to implement this efficiently. So that's this kind of parsing strategy that I showed here. If you look for this in the paper, it's called a stack LSTM. Really, the model here using RNNs to encode the context and the use of a stack are kind of independent tricks, but this is called stack LSTM because it's using this stack to be able to do this efficiently. And we have an example of this. This is the thing that I said was more interesting than the feed-forward parser. So now we can take a look at what this looks like also.
Yeah, so this is the stack LSTM. So you have your set of actions, you read in your vocab, you read in the correct transitions from the oracle. So after this, you're going to have every sentence is going to be paired up with a list of the correct actions. So if we come...
Oh, so
down to
sorry,
here.
we forgot to mention how we got the oracle, so maybe we should do that first.
Right. Okay, so do you have the slides for that, or do you want to do that?
Yeah.
We can also open up the oracle.
So there was a thing in the reading materials about how we calculate the oracle. We also have an example of this here in oracle.py, and this basically reads in, or maybe you can explain.
Right. So this reads in sentences paired up with their correct heads. So the way I'm formatting this is it has every word, then it has the correct head. And you want to take this and return a list of correct actions that you can use for your parsing algorithm. This is not the most efficient or well-written oracle, but it works, I think. So essentially what you do is you read the entire sentence into the buffer, and then if the stack is empty or only has one element, you cannot do a left or right reduce, so you have to shift. Otherwise, you compare the top of the stack, the head of that, with the location in the sentence of the element underneath that. And if that is indeed, if those are the same, that means the head of the top of the stack is the second element in the stack, in which case you can do a reduce. The same thing for the head of the second one in the stack being the top of the stack. You can do a reduce the other way that time. However, you need to make sure you're not accidentally reducing elements in the stack that still have like other words that have them as their head later in the sentence. Because if you do that, they'll be gone. So then by the time you shift the word that has them as the head into the stack, you can no longer reduce them and sort of subsume them in the correct element. So that's what these two checks after that are. You could probably do this a lot more elegantly than I did, but this gave the correct answers as compared to the data.
So I guess the important thing now is that we use this oracle, and this just outputs our data with 3 labels for each of, with basically actions and labels.
Right.
So this turns this into a classification problem where we don't need to worry about the trees anymore. It's like a sequence. It's kind of a sequence labeling problem, but it's a structured sequence.
Right. So when we go back to the stack LSTM and look at parse, this oracle actions is that list of actions. So this will look something like shift, shift, reduce left, shift, shift, reduce left, reduce left, reduce right, shift, shift, whatever. Then if we go up, we have the buffer RNN, the stack RNN, and a bunch of parameters. Something important to note is we also have an empty buffer embedding, and this is just something that helps a bit. When you push everything off of the buffer, there's still something there to return an output, so that you can still compose that with everything else. If the buffer was completely empty and we didn't have an embedding there, you wouldn't be able to return an output for that to compose with the rest of your functions. Then to go through the code, you look up all of the words and then append them all to the buffer, the embedding, and the vocab ID. Then this sort of steps through the sentence until both the stack has one element left and the buffer is completely empty. Make a list of valid actions, which is going to be either shift or shift and reduce right, reduce left. Or just reduce right, reduce left. Then as long as there are valid actions, as long as you're not done, you get the buffer embedding as, remember in the buffer we were storing them as a tuple. So you get the buffer embedding, the stack embedding, and then the parser state is just the concatenation of the buffer embedding, the stack embedding. You go through the 10H and you get either the max action, or if you have an oracle, you choose the correct action from that. Afterwards, you need to perform the action. So if you're performing a shift, you are going to move the top of the buffer to the stack. If you are doing either a right reduce or a left reduce, those are essentially the same action with the head and the modifier being swapped. So if you look here, this chooses the head and the modifier as either the left and the right or the right and the left, depending if it's a reduced left or if it's a reduced right. And then you sort of go through the example that Graham showed, where you're going to pop the top of the stack and the two top items of the stack, and then push back on whichever one is not the modifier. So you push back on the head. And that's the...
So it's this is more complicated than the things we've done before, but you can see it's still, several, I don't know, the whole thing is maybe less than 200 lines of code. And this is basically a state-of-the-art parsing algorithm for dependency parsing. So, yeah.
What is the functionality of the buffer LSTM?
So the buffer LSTM is encoding your entire input sentence. So if you don't have the buffer LSTM, you're sort of doing generative parsing. And this is a lot harder because you don't know what's to come in your sentence. But the buffer LSTM lets you know what's in the future, what's to come. So you can parse half of the sentence, but you know the second half.
Yep.
So it's essentially learning what might come in the future. Is that right?
Well, because we're parsing, we already know what's coming in the future. We already know the whole sentence, so we can use the future words to decide what action to do next. So, for example, if we see that there's a preposition coming up next, we will probably be wanting to shift.
Why LSTM? Why not normal stack?
I'll ask the same question. Why not LSTM? LSTMs work for almost everything. So. No, but we could just use the next three words, but we have all the words. We have LSTMs, which can learn things about variably linked sequences. So it seems like it should work.
Just sort of a quick note: if you want to change this into a feed-forward model for whatever reason, you rip out the LSTM part of this and you put in your feature extractor, and then your feed-forward network on top of that.
Right. So you can diff the feed-forward network versus the LSTM and see what the differences are here. I think you adapted the feed forward from the LSTM, so yeah. Did you have a question? No, okay. Okay, I'll move on to the next one. So shift reduce parsing for phrase structure. I talked about dependencies this entire time, but there's also phrase structure as well. Shift reduce parsing isn't used for phrase structure parsing as much for a variety of reasons, but it is still used pretty extensively. I looked up the first shift reduce phrase structure parsing thing, and apparently it was probably made here at CMU by Kenji Sage and Alan Levy. But that was just with a linear classifier, and I think Watanabe et al. Were the one, or Watanabe was the first one to apply it to neural models. So if we have a phrase structure tree like this, it basically looks very similar. The first thing we do is we binarize our tree. So we take all things with more than 2 children and turn them into a kind of right branching tree with only 2 children. And then we have actions like shift, and then reduce with the symbol, and also unary, so we can stick a unary on a unary symbol on like this. So basically, an entirely similar thing can be done for phrase structure parsing as well. Just you need to change your actions a little bit. You need to change your model structure accordingly as well, I'm sure, but the idea is pretty similar. One kind of interesting thing with regards to phrase structure is recurrent neural network grammars. These are generative models for parsing. So this is the opposite between, or the difference between this and the model I showed before is the previous model was a discriminative model. It tried to predict the tree given the input. This one tries to generate both the sentence and the tree at the same time. So what this looks like is you just have a non-terminal S, non-terminal NP, and then generate, when you do shift, instead of shifting, you generate a word, basically. So you generate you generate hungry cat, a VP. And this has the same kind of composition, etc., that was in the stack LSTM model. So why would we want to do a generative model? One of the really interesting things here is this can be used as a language model as well. You can use this to predict the probability of a sentence. You could also put this on the output side of your sequence-to-sequence model and have something that generates trees at the same time that it's generating a translation or a dialogue response or whatever else you wanted to generate. This gave good parsing results. So this, for a while, was the top performing parsing model on the Penn Tree Bank. But one important thing to know is that decoding, I shouldn't say decoding, sorry. Parsing is difficult, so it's not trivial to be able to parse with this well. So you need to generate, what it did was it generated with the discriminative model first and then did re-ranking. When you're calculating the language model probabilities, you also need to do something called importance sampling to calculate things. So I think this is a really good and elegant model, but it's a bit more difficult computationally, so be aware of that if you want to dig into this farther. So in terms of a simple approximation to what the recurrent neural network grammar is doing, there's also linearized trees. So the idea is it's very, very similar to the RNNG, but it just takes a tree and treats it as a symbol sequence like this. So if you have a tree, S, NP, NNP, you do pre-order traversal. So you take the top one first, then the left one, and you create a symbol sequence like this, and you can generate the symbol sequence using a regular sequence-to-sequence model. In fact, you could take any general-purpose neural machine translation system and train it on this data here, and it would do something for you. That's the great thing about this. It's super easy to apply. The bad thing about this is it doesn't have an explicit composition function, for example. It can't treat composed trees as a single vector, like the stack LSTM or RNNG can. This turns out to be really, really important for the stack LSTM or RNNG performance, and is probably the reason why the stack LSTM and RNNG perform better than these more simple models. The other thing is that it's not guaranteed to output well-formed trees. Like every once in a while, you'll get a tree where it doesn't have enough closed brackets or something like that. So what you do in that case is you just add extra brackets at the end, apparently. So it's a cheap hack to make this actually work properly. There are ways to fix this, but that tends to kind of fix the problem. So that's all for this time. That's a brief overview of transition-based parsing models. Are there any questions about this? I should emphasize, I talked about dependency trees and phrase structure trees. You can use these to generate any trees you want, of course. So if you have anything else in tree structure, you can try to use these models. Yeah?
I'm not sure about the recursive neural network model.
Yeah.
By Socher.
Mm-hmm.
In this model, they have a tree structure in the task type? Or?
Yes.
And then maybe the task is different from those of other models like stack LSTM and whatever.
Right, so this is, I should emphasize that none of the models in this section are parsing models. These are all models that assume we have a tree, and then based on that tree, learn the representations of our sentence. So all the other models I talked about are models that take in a string and try to generate a tree. These are just models that say, we have a tree, what is our vector representing that tree? So that is one of the reasons why you can't apply these trivially to like a generation task, for example. You couldn't create a language model with one of these. Anything else? If not, I will, I guess I'll finish up. Oh, sorry. Oh, how do you evaluate? Yeah, it's usually, so dependency parsing is actually relatively easy. It's attachment accuracy, which is for every word has one head. And it's just the accuracy of choosing that head. And then you have unlabeled attachment score, which is just whether you were able to choose the head correctly, and labeled attachment score, whether you chose the head and the label appropriately. For phrase structure parsing, it's harder because you have spans and you have spans. You can have unaries, etc. And there, the standard measure is phrase F measure, which is basically your F measure of generating a label for each span.
But in dependency parsing, there could be multiple choices on the sentence. So how does it can be considered in that?
Like, you mean the interpretation of this sentence is ambiguous?
Yeah, maybe regarding the context, maybe there could be one meaning, but just one sentence. We have just one sentence, but in that case, there could be multiple meaning and multiple representation.
So actually, you do not do dependency annotation on only one sentence. You do dependency annotation on the whole article in like in the Wall Street Journal in the Penn Tree Bank. So the annotation itself might be different for two different identical sentences that appear in the Penn Tree Bank, because based on the context, their interpretation changes. I don't know of any parsing model that actually considers that. I'm not mainly a parsing person, so there might be one that I don't know of, but I think almost always you just parse by the sentence. But I think the majority of the ambiguity is also resolved by the single sentence also, so it's not that bad. Okay. Okay. Thanks a lot, everyone. That's all for today.